Welcome back. My name is Alexander Breeze. This is my second video in the series of my attempts to prove P equals NP by finding a polynomial time solution to 3-SAT and 3CNF equations. This attempt wasn't actually polynomial time. It was just an idea for an attempt, which was exponential time, but maybe better than existing options. Also, turns out you couldn't see my cursor in the last video, so I have there's this laser tool, and that is what I will be using to show things. So the second attempt, we will call it split search. It is a recursive strategy. Essentially, we have n literals, so series literals 1 to n. The idea was you split it in half, so say less than half, less than n over 2, and greater than n over 2. And then you split the clauses into 3 groups. So either the clause has 3 literals which are all less than n over 2, or it has 3 clauses which are all greater than n over 2, or it has some mixture of that. And so as we can see, each clause has 3 literals, each literal is left or right. So 1 in 8 clauses will be all to the left, 1 in 8 clauses will be all to the right, and 6 in 8 will be in the middle. So we start on that, we split it into 1 in 8, 1 in 8, and the 6 in 8. And then we recurse on the 1 in 8 and the other 1 in 8. So each recursive call has 1/8 of the literals, and more to the point, it has 1/2. It has 1/8 of the clauses. It has 1/2 of the literals, and that's the important part, because it returns every possible satisfying assignment of those literals. So if we have n literals, then we get every possible solution of the first half of literals, and we have every possible solution for the second half of literals. So each one has a size of 2 to the power of n over 2. So this is 2 times that. And then, of course, we take the first half of the solutions, and we take the second half of these solutions, and we find some combination of these of one solution from each group, which satisfies the overall, the remaining 6/8 of the clauses. So now let's get into the problems with this. First off, this is big O, 2 to the power of n over 2 for each recursive call. So 2 to the power of n over 2 is essentially 2 times 2 times ... times 2 n over 2 times, which could be written out as a times a times a times ... times a n times, which essentially means that a times a is equal to 2. And equivalently, a is equal to root 2 equals 1.4. 1.4 something something. Obviously, it's an irrational number, so it never ends. But this gets us our first problem, because this means big O of 2 to the n over 2 is equal to big O of 1.4 to the power of n. Actually, a bit more than that, because it's, as I said, it's irrational. The problem is the best SAT solvers are 1.3 something something to the power of n. So that right there, that makes our solution not only exponential time, but worse than other existing SAT solvers, at least the best SAT solvers. The other issue, of course, is that once you have these two, you then have to cross multiply them. The naive way would be to try every solution in the first half with every solution in the second half. But of course, that would take 2 to the power of n over 2 times 2 to the power of n over 2, which would be 2 to the power of n. So that right there is literally as bad as the most basic SAT solver of just trying every single possible combination. But even if you could find some more effective way of finding valid solutions, which is difficult given that you're finding two of these that OR together to satisfy all instead of XOR, even if you could find some efficient way, you still have the issue of this is worse than this. So if it's a polynomial time SAT solver, it doesn't work. If it's an exponential time SAT solver, it's not fast enough to beat market leaders, which means it's useless, essentially, in terms of being worth something. So that was the second attempt, and that was this video. I hope it was informative. I feel I should explain what I meant when I said you OR these together, and why that's difficult. So essentially, this is this contains solutions to the first half of the literals, and this contains solutions to the second half of literals. When you add together any solution in the left with any solution in the right, you get one full solution for the all n literals. Now these 6/8 of the clauses, um, they contain literals in both groups. So you can write this out as saying which of the solutions in the first group satisfy these clauses, or which clauses here are satisfied by literals in the first group, and which of the clauses are satisfied by literals in the second group. Essentially, you take the clause, let's take this clause, all right? It has one literal in the left group, so you see if this solution satisfies that literal, and that tells you if it's satisfied. So essentially, you get a bit string for each solution here, and you get a bit string for each solution here, and you need any combination of these two solutions needs to satisfy the entire thing. So you need to find two bit strings, one here and one here, which OR together, not XOR, but OR, to satisfy every clause, which is difficult because if it's XOR, then it's similar to finding two integers in a list which add to a certain number. But if you're trying to find XOR, then it's significantly more complicated. So that's just explaining that.